Hi, everybody. Well, today we are in chapter 6, and we're moving up in the world. We're actually moving up a dimension. As you can see here, we're going to be working with some three-dimensional objects today, and we're going to find volumes instead of just area. Um, yes, but the first thing I need to do is a magic trick. So, 3, 2, 1. Oh, all right, Dr. Lindholm, why's your face so big? Make it stop. All right, we're gonna do a magic trick with these cards. Um, and the magic trick is um, find the volume of this deck of cards based on just one card. Now you can see, right, that this deck is a rectangular prism. How would you find the volume based on one of them? Well, one of the ways you could do that is just multiply the volume in one card times how many cards you have, 52 cards in a deck, and you would get the entire volume for the thing. Now, let's examine this for a little bit. I would like to call this a cross section because the idea here is we've got some appreciable area, but we have a very, very thin width here. And that thin width is going to be the dx it's going to be the differential that we're working with, the slight nudge in the x direction. But the idea for all of these integrals that we're about to do is we're going to find the area of a cross section, and then we're going to integrate in a direction that is perpendicular to the cross section to add up all of the cross sections together. And so, yeah, I guess with that being said, the magic trick was math all along. It was the friends that we made along the way. Anyways, let's get you on the right screen here. And we're actually going to do some math. So that's the idea. I guess I could scroll down here to the summary. Find volume using cross sections. We are going to develop a formula for the area of a given cross section and then integrate in a perpendicular direction. So we're going to come up with some area function for our cross section, and we're going to integrate from the smallest x value to the largest x value and add up all of those cross sections along the way. Okay, so for a sphere, the cross sections are going to look like circles, right? Let's click this. Oh, look, I already had it. Oh, and this is I actually already updated this. Look, oh, nice new bright colors. Right now, this one said a sphere of radius r. And maybe you're like, oh, Dr. Lundholm, I already know that the sphere of radius r has a volume of 4/3 pi r cubed. I memorized that formula since the days of my youth. We don't have to do this integral. We're going to do it. It's going to be beautiful. So we know the answer that we're hoping to get in the end. We're going to do it using an integral. And real quick, just to show you, in 3D, what this looks like. Yeah, right now our radius is 3, but I've just got the slider called x0, and x0 is going to, vary between -3 and 3. Oh, this is probably a better orientation. But yeah, notice that as you go along, we have a bunch of circles, but those circles are of different sizes. So as we describe the cross-sectional area, we're going to have to do that in such a way that, measurements vary according with the cross-section in a way that's good. Okay, let's open OneNote back up. And let's think about what we have. We're trying to set up an integral from, some x value to some x value. Now, in this case, the boundaries on our x values are going to go from r to negative r. Because, yeah, the sphere goes out to the radius. So our integral will be from negative r to r. And yes, there's some symmetry here. Indeed, what the function that we're going to come up with is going to be an even function. And probably we could do 2 times the integral from 0 to r. Yeah, let's keep working with this one. And maybe we can change it later. But yeah, what we need is an area function in here in terms of x, and then we're gonna have, the dx there, which is like the thickness of the cross section, if you want to think about it that way. This is gonna give us the area, dx is like thickness. And we need to come up with a function for, the area of that red circular cross section. Well, normally that is pi r squared, but notice that the radius of the circle is not the radius of the sphere the entire time. There actually will be a great circle when we go through the z-axis, and that one circle would have the same radius as the sphere. But so yeah, if we were at x equals 0, boom, we would have a great circle that has the same radius as the sphere. But yeah, when we're down this way, no way. That circle has a smaller radius than the sphere, and the radius is given by this vertical distance. Okay. So the vertical distance here, using the Pythagorean theorem, is the square root of r squared minus x squared. So, the idea here is we've traveled some distance x in the x direction. The radius is the hypotenuse of that right triangle. And so the height is the hypotenuse squared minus this leg squared, and then square root. So this is actually, I don't know, maybe we call this r, like big R rather than little r. And the area function would be pi r squared dx. And then, we could change this so that, we substitute all of that in for r pi times, well, it's going to be the square root, I should just write it, the square root of r squared minus x squared squared dx. And then that just becomes r squared minus x squared. Okay. And then, now the radius of the sphere is a constant. I mean, we can let r be anything, but yeah, the radius of the sphere is a constant. So this r we can treat like a constant. So what I'm going to do is rewrite this one more time. I'm going to bring the pi out front because that's a constant. But yeah, as we integrate, we're going to treat r squared like just a constant, no big deal. Okay. So yeah, take antiderivative. We'd have x times r squared minus 1/3 x cubed from r, or yeah, from 0 to r. Come on. All right, I'm getting over at the edge. And then, yeah, when we plug in r for x, we get 2 pi times r cubed minus 1/3 r cubed. And the 0 part would just be minus 0. So we don't even write that down. But anyways, now we've got 2 pi times 2/3 r cubed, and that is 4/3 pi r cubed, just like the formula that we memorized. So cool. We used calculus to do that. We added up a bunch of circles to make a sphere. That's super cool. Yeah. Moving on. Here we have another familiar shape. It's not too familiar because I haven't worked this problem in a while, but we've got a pyramid and it has a square base. So the sides of the square base are S. We've got a total height of H. We've got a little height here of Y that goes down to a cross section that is labeled with, square sides as X and X. So we're gonna find the volume of this square pyramid. All right, so the idea is, again, we're going to set up an integral where we have an area function of the cross section. And the area of this cross section is x times x. So, writing x squared here wouldn't be a bad thing necessarily. Except, I mean, we probably want to express that, in relationship to S and H. Goof. This is one of those times where probably would have been good for me to look at the answer before trying to go here. I don't want to waste your time. If you need to fast forward a little bit, I don't blame you. Let's do this. Okay, cross sections. Boom, 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 all the way up. The problem is, it looks like I kind of want to set up an integral dy here, because the cross sections, I feel like, I don't know, we're moving up this way. And yeah, we're going to be going from 0 to H. You know what? What if we set this up as treating this black line as the y-axis, and we set this up as an integral where we express this area function in terms of how high it is, how high the cross section is. Okay, I like where we're going now. So I think why we have this is because we're going to be able to use some proportions here. We've got some similar triangles going on here. So if I were to draw this green triangle along the slant, that green triangle would be similar to this orange triangle, where yeah, the orange triangle has a height of h, and well, I guess this would be s over 2 for the triangle that I drew. But if you drew a triangle over the entire thing, it could be s. Oof. I want to do the entire thing because I want the entire side length of the square. So excuse me for redrawing my drawing, but yeah, I want the triangle to go across the entire square. And so the green triangle is going to do the same thing. Oh, wow, that was bad drawing. Okay, boom. So green triangle is going that way too. So let's get rid of the s over 2. And so that would have some kind of slant height, but maybe we don't even have to figure that out. With the green triangle, that would be equivalent to y and x here. So this is weird. This is weird, but how I'm going to interpret this as like this is our initial y value, and if the y distance was all the way up there, we would be at y0, like y is equal to 0, and then y is going to keep getting bigger and bigger and get eventually to h once it reaches the bottom of this pyramid. So I'm going to start up top and then integrate down is the way that I'm feeling this. So starting from y equals 0 to y equals h in the end is the boundaries on my integral there. And then we need to come up with a formula for the cross section based on how far down we go. Okay, so the formula is going to be, the formula for the area of the cross section is x squared, but what is x squared in terms of y, or in terms of h and s? Come on. Oh, right. At the end, we would want this to be s. Okay. The relationship we have here is h over s is equal to y over x. That's proportion. And what we want to do is we want to solve for x. So let's cross multiply real quick and get h times x equals sy, then divide by h and get syh. Yikes. Okay. And so the area of the cross section is x squared. And so the area of the cross section is also s times y over h squared. Okay. Yeah. I'm down with that. Let's see what happens. We're going to integrate from 0 to h of sy over h squared dy. Now, at the beginning of this kind of a problem, you would pick a side length s and you'd pick a side or a height h. Those are going to act just like constants. So having an s squared over h squared out in front, I think that that's fine. And we just have the integral from 0 to h of y squared now dy. Let's do the integration. Oh man, if this turns out horribly, I am so sorry. I think we're on a good path here though. Yeah, so we're integrating with respect to y. 1/3 y cubed. That's actually a good thing. And yeah, 0 to h. So then bring it up here, and we're substituting in h everywhere where we see y. So s squared over h squared times 1/3 h cubed, and then minus the 0 again. But yeah, we get 1/3 s squared h in the end. And actually, that is the formula for the volume of a pyramid, or a square pyramid at least. You find the area of the base, and you multiply that times 1/3 of the height. And that's actually great. Oh. I'm glad when math makes sense. Okay, so that actually worked. And here I have, I don't know, a pyramid. And it's actually 1/3 of the volume of the parallelepiped that we have there. So I guess what I have here is just a pyramid of height, whatever I tell h to be. So right now it's height 3. But yeah, if I was in person, maybe I would have thought to brought, I've got some wooden blocks where you can fit 3 pyramids in one of these parallelepipeds, the rectangular prism kind of a thing. Anyways, that volume formula is good. Stop spinning. Yeah, so awesome. We found that volume of a pyramid, again, using cross sections. Now, what was key in order to be able to orient ourselves to this? I think one of them was we needed to imagine an axis and moving along an axis. So since this was oriented vertically, I just chose the y-axis. And then I wanted to do an integral from 0 to h because, we're going from 0 down to a height of 8. So thinking about those bounds and then thinking as the y value as part of the way through those bounds, just like here we were treating the x value as part of the way through the bounds. So yeah, the fact that this was x by x doesn't really make too big of a difference. Like, that's really just a placeholder for whatever that side length is. And we were able to find that side length by using similar triangles. So yeah, a lot of the time, if you're doing stuff by cross section, either you're going to be working in a familiar shape like a circle, and you're going to be able to, find a nice formula for the area of cross sections that way, or using similarity sometimes is the way to go. To help you figure out what those cross sections are. Okay, cool. All right, number 3. Oof. Okay, we've got a curved wedge and it's bounded by a right circular cylinder. Sure, so that gives us the curvy part. The XY plane and a second plane passing through the y-axis at an angle of 45 degrees to the XY plane. Cool. The cylinder's axis is the z-axis. Okay, so the cylinder is centered here on the z-axis. So this part on the bottom boundary is a circle, or a semicircle. The cylinder's axis is the axis and it has a radius of 2. What is the volume of this wedge? Woo. Okay. So again, the main idea is here, it's actually pretty easy to see that we're going to go from 0 to 2 in the x direction because we're starting off here at x equals 0 and going out to a radius of 2. And that should show up soon. Okay. And yeah, we're going to have to come up with an area function for what looks like a rectangular cross section at each point. Now, this rectangle, I kind of wish that I had a GeoGebra thing for this, but I don't think I do right now. Let's see if I can do horrible drawings real quick. We've got to imagine this rectangle changing as we go along. If we were to make a rectangle close to x equals 0, that rectangle would be relatively wide, but also short. And if we were to make a rectangle out towards the edge here, it would be relatively tall, skinny-ish. So the dimensions of this rectangle are going to change the entire time. Okay. We are given a pretty big hint here that, as we go along x units, the height of this rectangle is also going to be x because we have a slant of 45 degrees. So yeah, we've got a slope of 1 in that direction, kind of a thing. So yeah, we need to figure out what the area of this rectangle will be at all times. Okay. So the height of the rectangle is going to be x. Right? As we go along in the x direction, the height's going to be x. But the width of this rectangle is going to depend on how far it is to go out to, this y boundary on the right-hand side, or this y boundary on the left-hand side. And again, since this is centered at the z-axis, both of those are going to be symmetric. So really the distance that we're going here will be 2 times the square root of 4 minus x squared. So I think, okay, for the width of the rectangle, I'm going with 2 times 4 minus x squared. And so I think we have height times width here. And we could be good to go. Let's see what happens. For this one, it looks like the u substitution could be in order. If we set u to be 4 minus x squared, du could be minus 2x dx. And notice we've got a 2x on the outside. So, really what we're going to be doing is minus u du is equal to 2x dx. And then, we can substitute that in. I haven't figured out what the bounds are yet, so I'm just going to write x equals 2 and x equals 0 to remind me that I haven't changed those yet. But that allows us to substitute in du for 2x dx. And we just have a minus sign to bring in. And then we have the square root of u du as, yeah, the integral that we need to solve here. Okay, that looks pretty good so far. Now I want to take an antiderivative, and I'm normally one who likes to change my bounds into terms of u as well. So we add 1 to the exponent and divide by that. So 2/3 u to the 3/2. And the boundaries on u will be if we plug in 2 into this equation, we would get 4 minus 2 squared, which is 0. And if we plug in 0 here, we get 4 minus 0 squared, which is 4. So now those boundaries are in u. And we can keep going. Let's see. So this means that we've got minus 2/3 times 0 squared. That, and then we're going to subtract off, oh geez. But really, since we've got a minus sign out front of here, we've got negative 0 minus negative 2/3 times 4 to the 3/2. Okay. So now we've got 2/3 times 8, and we get 16/3 in the end. And good grief, I don't even know if that's true. I mean, I think we did good. Let's check real quick, just to, do I have this open somewhere? Let's see. Ooh, that's what we're gonna go to next. Just to make sure. Okay, no. Here we are. Yes, dude. Okay, 16/3, answer confirmed. All right. Yeah, we're good. Those changed along the way, those cross sections changed shape along the way. But as long as you get a reliable area function for those cross sections, you're going to be golden. We used to use sub. All right. So, in summary, find the cross section. Yeah, find a formula for the cross sectional area, and then integrate in a perpendicular direction to those cross sections. Cool. So now we're getting into section 6.2. And really, I mean, I guess, all right, we're 34 minutes into this. We're going to talk about creating volumes of revolution. So now the idea is we've got this leaf shape. And this leaf shape, if it was just itself in the XY plane, we could find its area either using dx or dy at this point. You know, if we were going to do an integral in terms of dx, here, let's see. Let's draw leaf shape. Actually, leaf shape with 2 different colors. Yeah, if we were going to do this with dx, we would be orienting, you know, the rectangles in our Riemann sum this way, and we would be integrating from some starting x value to some ending x value, and yeah, the integral would look like oh, here, let's name this one A and this one B. It would be the integral from A to B, where we would be doing the top function minus the bottom function. And yeah, it would be in terms of dx. So that would be great. We could also alternatively do this using dy. I know that we haven't done it too much, but let's do this and this again. Yeah, now if we were going to do this with dy, our rectangles would be lying on their sides and we would be imagining to, add up this way with a bunch of little rectangles. And, if we labeled this as, I don't know, y equals c, and this one as y equals d, we would be using the integral from c to d of, we would have some function of y, here, let's label it h of y. That's kind of like our top function since it's further away from the x-axis or the y-axis. And the red function is like our bottom function since it's closer to the y-axis. So h of y minus, what letter? W of y, we'll call that function w, and this would be dy. So why did we just look at that? Well, when we use this area and sweep it around the y-axis as an axis of revolution, we're going to make a volume with this as a cross-sectional area. And depending on which way we orient the tiny little rectangles that we would be using here, where on the first one, our little tiny thickness is in the x direction. And on the second one, our little tiny thickness is in the y direction. Those are going to give us different shapes. Let's go to GeoGebra. Okay, so now we're in GeoGebra 3D. And yes, I have graphed this cross-section in the XY plane. When I allow this to go around, it sweeps out a volume. Isn't that cool? All right, and the volume at all times has a cross-section, just like that leaf shape. So, we've got some kind of a cup going on with a horn inside of it. Now, if we, let's say, use this one. All right, so if we, as we're rotating around the y-axis, if we orient our little rectangle vertically like this, so that the width, the little tiny nudge width is a dx, it's a little change in x, notice what kind of shape we get. All right, so we're going to rotate this thing around. And at each point, I've got the trace on for the little segment that we had. So when we bring it back, it traces everywhere where that little blue segment has been. And what we call this shape is a cylindrical shell. Because, if you were going to make a cylinder, this could be like the lateral surface area of a cylinder. And notice we could get different size shells if we moved our cross section up a bit towards the edge here and we swept things around again. We would get another shell. This time the shell is, maybe a little bit shorter than the original one that we did, but it also has like a bigger radius for that last one. Okay. The idea is if we add up a bunch of these shells, we eventually get the entire volume. And so this first way of doing things is called finding volume using cylindrical shells. The key thing here is that the what do we want to call this? The little tiny segment, our line segment is oriented so that the thickness, the little tiny thickness, is along the x-axis. And so, I don't know, the long side of this segment is parallel with the axis of rotation. And whenever the segment is parallel with the axis of rotation, we're going to get cylindrical shells. On the flip side, if we go down here and create the segment that is perpendicular to the axis of rotation, and this is the one that, if we were going to come up with an area integral here, we would be integrating, with dy as a differential, because we would be, adding from y equals 0 up to y equals 1. But yeah, if we use one of these and then we spin everything around the y-axis, we're going to get a different shape. Boom. Here we get a washer. Just like a washer that you would use when you're, I don't know, fastening something with a screw and a bolt. It's a washer. And the characteristics of a washer is that you've got some inner radius where nothing is happening, and then you've got an outer radius where, the area that you're actually trying to get is. So you're always going to have an outer radius minus an inner radius to come up with the area of the washer. So maybe the washer is even a little bit easier to see than the cylindrical shell in terms of how you would add multiple, versions of this to get the entire volume. Because this is a little bit more like the volume by cross sections that we've just been looking at. These ones look very much like circular cross sections, except, you're cutting out a middle circle in the middle because, well, there's no volume there in this given shape. So this looks a lot like volume by cross section. Cylindrical shell is that way too, except the cross sections are parallel to the axis of rotation rather than perpendicular to the axis of rotation. But yeah, let's go and back to OneNote so that we can look at the details again. So yeah, we're spinning around the y-axis here. This one would give us a shell. And the right-hand one would give us a washer shape. But, if we were going to make a different shape, now this is it's a different problem. But if we were going to rotate around the x-axis instead, this one would give us a washer, cross section, and this one would give us a shell. cross section. Because again, now the segment would be parallel to the axis of rotation there, rather than perpendicular. Anyways, so it's not always going to be the case that dx is a shell and dy is a washer. It depends on the orientation with the line segment and the axis of rotation. If they're parallel, shell. If they're perpendicular, washer. Yeah, here are some drawings. Cool. And yeah, for each time, we want to come up with the area of each one of these cross sections. For the cylindrical shell, it doesn't seem like an area right away, but what you do is unwrap this shell, cut it, so that you've got a height, which in this case, the height would be the distance between the top function and the bottom function. So top minus bottom gives us the height of the cylindrical shell. And then the length of the cylindrical shell, you can unwrap it, and the length of that will be 2 times pi times the radius of the cylindrical shell. The radius in this case will just be whatever x value you're at. So let me go ahead and draw that in because that's not there right now. But yeah, that's the radius for this one. Right now would just be the x value, and the height would be, yeah, top minus bottom. Okay, so what that does is it tells us to find the area of this. We look at it like it's a rectangle, and we do this kind of multiplication where it's 2 times pi times the radius times the height. So, you know, in general, this is going to look like 2 times pi times the radius of the shell times the height. So 2 pi r h. Let's go ahead and just, you know, write that. 2 pi r h is generally going to be the area of like the label, the cylindrical shell. Cool. So that's going to be fundamental to, you know, the formula that we end up using here. Let's go ahead and look at the details here, and then we'll come back and do the washer. So for this one, since the top function is y equals the square root of x, and the bottom function is y equals x squared, we do 2 pi times x, which is the radius of our cylindrical shell, and then times the height, and the height is the difference between the top and the bottom. So top function minus bottom function, throw a dx there on the end, and we're integrating from 0 to 1 because that's where those two functions intersect. And then solving things down, we use the power rule in reverse. Boom, boom, boom. And eventually we get down to 3/10 pi as a volume for that shape. So that's cool. On the other hand, we have a washer method for this same volume. In this case, to find the area of this blue washer, what we need to do is pi r squared for the big circle, and then subtract off pi r squared for the small circle. And so I've made the big radius big R and little radius little r. And so, yeah, each time we're going to be subtracting 2 circles, the area of 2 circles from each other. Shorthand, we can pull pi out and throw it out front. So we're always going to be, yeah, doing the outer radius squared minus the inner radius squared. And we just need to make sure that our little line segment is oriented such that the line segment is perpendicular to the axis of rotation. So this time we're doing dy because our axis is the y-axis. And then, yeah, again, we're going from 0 to 1. In this case, we're counting this 0 to this 1. And as you go along, the squared root of squared works out really nicely there. And eventually you get to the same answer of 3/10 times pi. So yeah, I think this is probably where we're going to call it for today. We were able to do the volumes by cross section, a bunch of slices all in a row. And then we introduced the shell and washer methods for volumes of revolution. And definitely we're going to do more examples of this. We've got, that paraboloid, and we've got that kind of cool coney shape. We've got another thing that looks pretty similar to what we did before. So there are a lot of examples that we could do. I think we're, moving on to an example like this where the axis of rotation is not necessarily one of the principal axes. That one will be, an example like that will be good. To think about the radius of the shell a little bit harder there, but yeah, we have the fundamentals down of the idea. Just to recap and finish up, the shell method, the segment, so the little line segment is parallel to the axis of rotation. And yeah, in general, the formula will be 2 times pi times the radius times the height. And here we get an x minus L. What is this L thing? Well, here we are revolving around the line x equals L. So this is a shift in the axis of rotation so that it's not just the y-axis, it's actually, which is x equals 0, it's the line y equals L. And so this minus L just adds, or well, subtracts, depending on where this line is, it adds or subtracts units onto that radius. It pretty much centers things so that this line is the new axis of revolution. But then you're multiplying that times f of x, where f of x is the height of the shell. In the case of what we just did, the height of the shell was actually the difference between two functions. This is actually just a little bit of a simpler formula, where this one's not necessarily accounting for two different functions giving you the boundary. This is just one function down to the x-axis. So this is a little bit simpler. Okay, so that's the shell method. The disk and washer method, disk, I haven't even really said that yet, but disk is just what you have if you don't have an inner radius that you need to cut out. Like if you've got a totally solid object, you wouldn't have an inner radius. The inner radius would just be 0 the entire time. But in this one, there was an inner radius because, yeah, the middle part of this volume was, empty. Yeah, this is for when the line segment is perpendicular to the axis. So line segment perpendicular to axis of rotation. And yeah, this is the same formula, except the washer is just a little bit more complete. It has an outer radius and an inner radius, but it's fundamentally pi r squared because you are subtracting a smaller circle out of a larger circle. All right, so with that, we're wrapped up. See you guys tomorrow. Bye.